Right, so our next speaker is Jafar from KU Leuven. Take it away.
Thank you for the introduction. Good afternoon, everybody. In this presentation, I'm going to first give you some background information on the notion of obligations and permissions. Then I explain the problem. After that, I provide a solution for that problem. And at the end, I refer to some further words. Okay. Concurrent programs allows maximum utilization of CPU and handling multiple events. However, they introduce new issues such as data race and deadlock. For example, here we have a data race where two threads writes on a same memory location concurrently. Or here we have deadlock where thread 1 is waiting for channel 2 to receive a message from thread 2, and thread 2 is waiting for channel 1 to receive a message from thread 1. So thread 1 is waiting for thread 2 and thread 2 is waiting for thread 1. There is a circular dependency here. One possible way to actually address these problems is using modular formal verification, where we assign permissions and obligations to each thread, and then we make sure that each thread only performs the actions for which it has permissions, and also each thread discharges all of its obligation before it terminates. For example, here, we need to make sure that any thread who tries to access a memory location has an access permission for that location. And since this permission or this capability, there is only one instance of this capability in the system, then this thread is assured that it is the only thread that can write on this memory location, so it can safely write on this memory. And this actually permission is obtained where this location is allocated. So here in the main thread, after allocating this location, it has access permission to that location, and then it gives this permission to this thread. Then this thread can successfully verify. But however, at this point, it doesn't have such a permission anymore, so it cannot pass this permission to this thread. So at the end, this thread cannot be verified. So this program, which is subject to data race, cannot be verified. What about deadlock? So here, this thread tries to receive a message from this channel. We need to make sure that if a thread tries to wait on a channel, there is another thread in the program that sends a message on this channel. Or in other words, somehow, because otherwise this thread will be blocked forever. In other words, when a thread, if a thread tries to wait on a channel, there should be another thread in the system holding an obligation for CH, where an obligation for CH can be discharged by sending a message on CH. In other words, when a thread tries to receive a message from a channel, it should spend a credit for that channel, where a credit can obtain by loading an obligation for that channel to the bag of obligations. And that obligation can be discharged by sending a message on that channel. And this way we have a modular verification. So this thread doesn't need to know about the other threads in the program. The only thing that this thread requires is a credit. So this credit assures that there is another thread who sends a message on this channel. But how this credit is obtained? So this credit, so here is the verification of the main thread. So as you see in the beginning of the verification, it doesn't have any obligation. Then it creates a new channel. After that, at this point, it obtains a credit for this channel by loading this channel to the bag of its obligation. Then it forks thread 1 and it passes this credit to thread 1. And here it still has an obligation for this channel. And at this point, it can actually pass this obligation to thread 2, where this obligation is discharged by sending on this channel. So here we verified this program, deadlock freedom of this program, in a modular way. We also need to take care of the circular dependency. So to avoid circular dependency, one common idea is to assign levels to each channel and make sure that each thread waits for channel in ascending order, or each thread waits for channel in descending order, one of these. So here we introduce this precedence relation, and we make sure that if a thread tries to wait for a channel, then it has spent a credit, and also the level of this channel is lower than the level of obligations of the current thread. Without this extra precondition, this program, which is deadlock, can be wrongly verified. Because here, when this channel is created, so here this program first receives and sends, which is deadlock. So here it creates a credit and obligation for CH. This credit is spent by this receive, and this obligation is discharged by this send. And this program is wrongly verified. Having this extra precondition, then at this point, it cannot proceed anymore because the level of CH is not lower than the level of CH. So this is how people verify deadlock freedom of program in a modular way. So it's possible to prove that any program which is verified by these rules is deadlock free because these rules preserve these invariants, and it's easy to prove deadlock freedom of the program having this invariant. Let's skip the soundness proof. Okay. But what's the problem? The problem is this program. Here we have a client-server program where server first receives a client's request, consists of the request and a channel from which the client expects to receive the response of the server. After processing this request, it sends the result to the client's channel CH prime. Here in the client side, client first creates a new channel CH prime, sends its request along with this channel to the server, and then waits for the response of the server. This program is deadlock free. The question is that how can we verify this program? Now let's forget about CH prime. Here, server tries to receive from CH, which means that it requires a credit, and client sends on CH, which means that it can discharge an obligation. So like before, we obtain a credit and obligation in the main thread and pass this credit and obligation to server and client. But what about the CH prime? Here in the servers, it sends a message on CH prime, which means that it can discharge an obligation for CH prime, and client tries to receive on CH, which means that it requires a credit for CH prime. The question is that, can we, just like CH, obtain an obligation and a credit for CH prime in the main thread and pass these obligations and credit to server and client? The answer is no, because the main thread has no idea about CH prime. CH prime is created in the client. Additionally, assume that these server and client are going to communicate, for example, they're going to send 10 messages to each other. Then at this point, 10 credit and obligations should be loaded in the main thread, which is not a good design. So this thread doesn't need to know about the number of messages passed between client and server. But again, how can we verify this program? So we have a solution for this. So here in the client, when it actually creates CH prime, if it loads a credit, an obligation for CH prime, and sends these obligations along with its request to the server, then this obligation can be discharged by sending on CH prime, and the remaining credit can be used for this receive. And this way, this program can be verified. So the idea is to transfer an obligation of CH prime over this channel. So it seems working. Let's go to define new proof rules. So for new channel, we only need to specify, when a channel is created, we need to specify the obligations which are transferred through this channel. And for send, when a thread sends on this channel, we need to discharge this obligation, which is denoted by T. And in the receiver side, we just need to load these obligations to the bag of obligations of the receiver thread. This approach is actually broken. These proof rules are not sound because if there is no receiver in the system, then the sender thread discharges some obligations which never are loaded to the system again, which violates our desired invariance. Additionally, even if there is a receiver in the system, there might be a state of the execution where these obligations are discharged but not loaded to the receiver thread yet. So to actually solve this problem, what is the main idea? So similar to the notion of obligations, we introduce a notion of importers. So each thread has a bag of obligations and also have a bag of importers. And this bag of importers indicates the channels which import some obligations to the current thread. For example, in the client server, the importers of the server is CH, because CH imports an obligation for CH prime. Then similar to bag of obligations, when a thread terminates, the bag of importers of a thread should be empty. And also we need to make sure that if a thread waits for a channel, the level of this channel is also lower than the level of obligations which are going to be imported to that thread. Additionally, we need to make sure that when a thread sends some obligations on a channel CH, then this channel is in the bag of importers of another thread in the program. And to enforce this rule, we need to make sure that when a thread sends some obligations on a channel CH, it actually spends a transferring credit or a transit for that channel, where a transit for a channel can be obtained by loading that channel to the bag of importers of the thread. And this importer channel can be discharged when a thread receives an obligation from the corresponding channel. So we define the sound proof rules here. So when a channel is created, we specify the obligations which are transferred through this channel, and also we specify the level of the channels which are possibly imported through this channel. We call it T prime. So when a thread sends a message, we make sure that the level of the obligations which are transferred is in T prime. And also we make sure that if this thread is gonna send some obligation on this channel, then a transit for this channel is consumed. And also the obligations are discharged. And in the receiver thread, we actually load the transferred obligations to the bag of obligations of the receiver and discharge the importer CH from the bag of importers. So here, that's how we can verify this program. So here, since this program is gonna send some obligation to CH, it requires a transit for CH, which is actually consumed by sending on CH. And this transit is actually obtained in the main thread, where it obtains a transit for CH by loading CH to the bag of importers of the thread. So we pass this transit to the server, and we pass this importer we pass this transit to the client, and we pass the importer to the server, where it's discharged by receiving on CH. So this program is successfully verified. Again, there are some invariants and a proof for soundness of the approach. I'm not going to go to detail. We also succeed in verifying some other variations of client-server program, where a server keeps serving clients until receiving a shutdown message. So here, in this example, CH transfers an obligation and a transit for CH prime, and CH prime transfers an obligation and a transit for CH. We also verified this variation where a server keeps serving clients infinitely. We also introduce another mechanism which allows to transfer some obligations through notifications. So here, these notifying threads can transfer parts of these obligations and transfer them to the waiting thread. And this way we succeed in verifying a number of interesting programs such as fair mutex, fair readers, writers, and dynamic philosophers. So to conclude, we introduced two mechanisms for transferring obligations through channels and notifications. We also encode the proposed separation logic-based proof rules in the very fast program verifier and succeeded in verifying a number of programs. And an interesting future work would be to integrate these two mechanisms together. That's it. Thank you for attention, and I'm happy to answer your questions.
Okay, great. We have plenty of time for questions. There's one at the back there. Do we have any volunteers with mics?
Hi, thank you for your talk. So can you clarify a bit, because this looks similar to type systems by Kobayashi for deadlock freedom. They also have obligations, capabilities, and this is the way of ruling out circularities that you find in deadlocked programs. So do you have any ideas on whether there is a relation?
So firstly, as far as I know, in Kobayashi's work, the sending, both sending and receiving on channels is synchronous. But here we have asynchronous channel, so which means that in Kobayashi's work, no obligations, there is no state where obligations are discharged but not loaded in the receiver because it's synchronous. So when it sends, it is blocked or it's immediately received by the receiver. So this problem doesn't arise there. I think that's one of the differences between this.
Any more questions? Yes.
I didn't catch whether the user of this tool would need to write any annotations to verify the program, or is it automatically?
At this point, it's not automatic, so you need to annotate your source code with some annotations. And for these specific programs, for the client-server program, you firstly need to specify the contracts of the client-server, which obligations and which credits are discharged and required to verify the program. Additionally, you need to specify the levels of the channels, and also you need to specify the obligations which are transferred through each channel. And lastly, you also need to specify at which points an obligation and a credit for a channel should be loaded to the system.
Okay, thank you.
We have time for one more while our next speaker sets up. Any more questions? I think I had a question. This is a naive question because I don't really know the area, but is this the sort of problem that one could also approach using session types?
Sorry.
Is this the sort of problem one could attack using session types?
To solve this in second time?
Session types.
Session type. Yes, so it's somehow related to session type, and but as far as I know, there things have been automatically done. Okay. But one of the advantages of this work is that you have more flexible, you have defined some more powerful preconditions and postconditions. You can customize your specifications according to the program.
Thanks. Okay, let's thank our speaker.